All right, it's time to round out our collection by talking about the arccotangent, the arcsecant, and the arccosecant, or the cotangent inverse, secant inverse, cosecant inverse. Or we could say the inverse cotangent, the inverse secant, the inverse cosecant. All right, we're going to start, as we did with the other graphs, by reminding ourselves what the graphs of the original functions look like. So for the first one, we're going to do cotangent. And tangent, remember, went something like this, but cotangent did something like this. If you think about this for a second, it goes through here and is asymptotic at pi and at 0. I didn't do a very good job with that, the top half of that. Let me try that part again. So we have asymptotic function, and the same way that tangent was asymptotic, cotangent is asymptotic. Cotangent goes through pi over 2, 0. So inverse cotangent is going to go through 0, pi over 2. Cotangent goes, well, let's see. It goes through pi over 4, 1, and 3 pi over 4, negative 1. So inverse cotangent is going to go through pi over 1, comma, pi over 4. Let's make this our 1. 1, comma, pi over 4, and negative 1, comma, 3 pi over 4. So our inverse cotangent graph looks something like this. It's asymptotic at y equals 0 and at y equals pi, in the same way as cotangent was asymptotic at x equals 0 and x equals pi. This is a single, so this is an asymptote down here as well. And where there's an infinite number of pieces of the cotangent curve, there's not an infinite number of pieces of the cotangent, there's an infinite number of the cotangent curve, but there's not an infinite number of the arccotangent curve, because if there were, it wouldn't be a function. If there was another piece of the curve up here, then this relation would not pass the vertical line test. So this is the only piece there is to cotangent inverse. All right, let's talk about secant. I just decided to go ahead and do my asymptotes and axes for both the secant and the cosecant graphs while I was in there. Secant, remember, comes from cosine. So if you imagine, I'll draw a cosine function in here. Cosine does something like this. So it's going to come down to here. Okay, and secant comes from that in that it's 1 over that graph. So I'm going to have something that looks like this, and I left one of my asymptotes off. Let's put that in where I used to have a 0 for cosine. Secant is 1 over cosine, so that would be 1 over 0, which means I have an asymptote there. And I think I'll put in another half of a loop there. Now I'm going to go back over this in a different color because I want to point out that just like the other graphs that we've talked about, this one will not pass the horizontal line test. So we have to pick pieces of this function that will allow us to talk about an inverse of this function by way of the pieces that we pick will collectively pass the horizontal line test so that the inverse will pass the vertical line test. So I'll say, let's pick this piece right here, but I can't pick this piece right here because that would fail the horizontal line test. Your book says that the next piece is this second half, if you will, the right-hand half of this next sort of first downward loop here. In other words, they're saying that this pink graph, what you see in pink here, is the graph on which we should base the domain restrictions for graphing arcsecant or inverse secant. And the claim that they make is that the reason for that choice is that it has to do with consistency in choosing the sine, S-I-G-N, when computing values for arcsecant. I am a little confused by this, actually. That doesn't mean it's wrong. It's just not something I have really ever seen before, and I'm not entirely sure it makes sense. Most of the time, you see the domain for secant restricted to these two pieces, so that the arcsecant still passes the vertical line test. Secant passes the horizontal line test if you restrict it to these two pieces. Therefore, secant will pass the vertical line test. All the values that secant takes on are attained at some point or another. So I'm not really sure why the textbook uses the two values, the two pieces of the secant graph that it does for its domain restriction. But you could argue, I suppose, that either one is correct. So what does this tell us about the graph of arcsecant? Well, wherever I have a vertical asymptote for a function, I'm going to have a horizontal asymptote. It looks like I have one at pi over 2. So I'll put a horizontal asymptote there. There's pi, and then 3 pi over 4 is here. I don't have pi over 2 and 3 pi over 2. I don't have pi over 2 and 3 pi over 2 labeled in the secant graphs. They're here and here. That's pi over 2 and 3 pi over 2. So I'm putting those, what used to be vertical asymptotes, in as horizontal asymptotes, and then I'm going to look at these values. The graph of y equals the secant of x goes through 0, 1. So I'll graph 1, 0 on the arcsecant graph. And then secant, from that point, secant goes out away from the y-axis and then eventually curves and goes up infinitely in the y direction. So arcsecant is going to go away from the x-axis and then carry on infinitely in the x direction. So that's that curve there. And then secant also goes through pi negative 1. So that means negative 1 pi, and then another point on my arcsecant graph. And secant then, from that point, comes back towards the asymptote that's less than that pi value, comes back towards that asymptote and down in the negative direction. So it's going to come back towards this asymptote and then in the negative direction. So that's what arcsecant looks like. Cosecant, let's see. Cosecant comes from sine. So where I had something that looked vaguely like this, for cosecant, I had something that looked like this instead. And of course, we have multiple sections of the graph. And for restricting the domain here, let's take this side. Let me get my thicker pen here. Let's take this side of this curve, and we could then take, we can't take this side because then cosecant, inverse cosecant would not be a function. This wouldn't pass the horizontal line test. So we need all the values that cosecant takes on are met here. Starting at 1, they go on forever. So as long as I've captured every value from 1 up, I'm satisfied. That's the only part I need. But I also need to capture from negative 1 down. So the question is, which piece should I use? And I like to use this piece here because it sort of gives us that symmetry again around, well, actually around the line y equals x, but also around a different kind of symmetry around the y-axis. So let me add my axis marks. Where x had a negative pi, a 0, a pi, and a 2 pi, y now has, I didn't mark it as a negative pi, but a 0, and then a pi, and then a 2 pi. Where y used to have a negative 1, a 0, and a 1, now x has a negative 1, a 0, and a 1. And where I used to have vertical asymptotes at 0, pi, and 2 pi, I now have horizontal asymptotes at those values. So I've got my axes and my asymptotes labeled. Let's look at some values for cosecant. Cosecant goes through pi over 2, 1. So inverse cosecant is going to go through 1 pi over 2. Then the graph curves toward the y-axis. So this one's going to curve toward the y-axis, but then it gets infinitely large. And on the other side of the y-axis, we have negative pi over 2, negative 1. Looks like I need to include negative pi over 2 down here. There's negative pi. And so I'll put an asymptote in there. Don't really need it, but that's okay. Negative pi over 2, negative 1 for cosecant becomes negative 1, negative pi over 2. So I have a point right about there. And then from there, the graph comes toward the y-axis and gets infinitely large in the negative direction. So I'm going to come toward the x-axis and get infinitely large in the negative direction. So that's what the graph of inverse cosecant looks like. Your textbook also uses a different, maybe I'll just do it in 2 different colors. For secant, your textbook says it wants to use this sort of right-hand leg of the second cycle, the second part of the first cycle of secant. And for cosecant, it wants to use, let's see, the first positive, I'll color them in both green and pink maybe. Okay, so we get green, either the green pair or the pink pair. And for cosecant, we get, see if I've got this right, that one and this one. Okay, so again, in green, I'll do a slightly smaller pen, however. Your textbook's version of secant inverse is this part, which matches ours, and then it's using the other half of that other loop. So we get that combination. So either the yellow pair or the green pair. I prefer the yellow pair. Your textbook is using the green pair. So I'm graphing them both. I'm showing them both to you because they're both correct. It's kind of, I guess, a matter of personal choice. For cosecant inverse, your textbook is using this. I want to cover it up. This is its first half, or one of the 2 pieces of the graph. And the other piece is 3 pi over 2. And it goes from here back. So you're either using a right-hand side and a left-hand side as drawn in green, or a right-hand side and a left-hand side as drawn in yellow. A right-hand side and a left-hand side, or in yellow, a right-hand side and a left-hand side. It's your choice. My choice would be the yellow one. I'm going to slightly modify the graph. I'm going to take those green ones out again just to alleviate any confusion, and we'll leave our final screen looking like that. I think it's worth mentioning, actually, that there are places in the world of mathematics where not everybody agrees. Most of what we've talked about in terms of graphing the, restricting the domain and graphing these inverse functions is down to convention. And so there are going to be sometimes variations in those conventions. That doesn't mean one convention is right and the other is wrong. It just means that they're different. And it's worth knowing that that sometimes comes up, especially since in the world of mathematics, we tend to think that there's only one right answer, right? There's only one absolute. Mathematics is absolute. That's not entirely true. There's disagreement all the time about what the right way to do something is, or how to prove a theorem, or how to graph an inverse function. Those things do happen. So I'm actually kind of glad this came up. It's worth noting that not everybody agrees about every single little thing. Now, you won't be expected to do much with these graphs. I wanted you to see them. They're part of the content of this section in the textbook, but there's really not much that I'm going to ask you to do with them. You'll have to do some exercises around them, but beyond that, you won't see them in quizzes or an exam, but you will see sine, cosine, and tangent inverses in quizzes and exams. One thing you will be asked to do is to use sine, cosine, tangent, cotangent, secant, and cosecant, and their inverses to do compositions of functions. We've done sine of sine inverse and sine inverse of sine. We've done that with cosine. We've done it with tangent. What we haven't done is, say, for example, the sine of the inverse tangent of a value, or the inverse cosine of the cosecant of an angle, right? So that's what we're going to talk about next. All right, composing sine with sine inverse, tangent with tangent inverse, those were pretty straightforward in that the answer is always just the input, as long as the input falls within the right range of values. If it doesn't, we have to adjust things and find an appropriate sort of substitute value. But the problem is otherwise fairly straightforward. These problems are a little less straightforward. I missed my inverse notation there. But they're not hard either. If you take a look, that what we're doing here is finding the cosine inverse. I was using the wrong pen there. Hang on a second. Finding the cosine inverse of a value. Let's draw a set of axes. And then let's notice that the value we've been given here is positive. So since cosine is adjacent over hypotenuse, and hypotenuse is always positive, the adjacent side must be positive as well. And in this case, that means my adjacent side is out here, use a different color, on the x-axis. Because if it were over here on the negative x-axis, then my adjacent side would be negative, right? Let's put the other side of my triangle in. So there's my right triangle. And I know that the adjacent side of this triangle is 11 and the hypotenuse is 15. Because I've been told the cosine inverse is 11 over 15, and what the cosine inverse is the angle whose cosine is 11 over 15. Well, here's the angle whose cosine is 11 over 15. Now, do I need to find that angle in order to answer the question? No, I need the cosecant of that angle, whatever it happens to be. And the cosecant is just 1 over the sine. So if I can figure out what the sine of that angle is, I'm trying to rewrite this and I'm having trouble. 11 over 15. If I can figure out what the sine of that angle is, this is an angle, right? I'll highlight it again. This is an angle. The arccosine is the angle whose cosine is 11 over 15. So I'm looking at this angle right here, and I want the cosecant now, or the 1 over the sine, so I want the sine of that angle. Well, sine is opposite over hypotenuse, so I have to go figure out what that opposite is. Fortunately, I know Pythagoras, so I can say that that value is just the square root of 15 squared minus 11 squared, which is 225 minus 121, square root of that, which is a square root of 104. I think that's as far as I'm going to get. Let's see, 104 is 2 times 52. I can reduce it. 2 times 26, 2 times 13. Okay, so I get a pair of 2's and then a 2 times 13. So 104, the root of 104 reduces to 2 times the square root of 26. I'll erase my scratch work here. So that means that that missing side has a value of 2 root 26. And now I can find the sine of this angle, because sine is just opposite over hypotenuse. So let's do, this is 1 over opposite 2 root 26 over hypotenuse. 1 over a fraction is just the reciprocal of the fraction. So the answer to this question is 15 over 2 root 26. All right, that's probably felt fairly circular, but let's just maybe walk through it again. I'm asked for the cosecant of the arccosine of a number. So I'm just going to focus on the inside at the moment. What is the cosine inverse of 11 over 15? Well, cosine inverse is the angle whose cosine is 11 over 15. In other words, cosine of theta is 11 over 15. What is theta? Or cosine of x is 11 over 15. What is x? So since we don't know the angle, we can set up the cosine. adjacent over hypotenuse, and we can use the fact that this is part of a right triangle to find the third side. So we don't actually evaluate this arccosine. We don't get a number for this. We just use the fact that these are two sides of a right triangle. We can find the third side of the right triangle, and we can use that to find the sine. The sine of, this is an angle, the sine of that angle is 2 root 26 over 15, opposite over hypotenuse. Once we know the sine of that angle, since cosecant is 1 over the sine, 1 over that fraction is just the reciprocal of the fraction. So this is my answer. Now we have to be careful because cosine is the value of cosine we're given here is positive. All students take calculus. So there's another place down here where we also have 11 over 15, and the angle is the same size, and the cosine of that angle is still 11 over 15, positive 11 over 15. So we need to ask ourselves, could this be a second angle? And it's certainly a second angle that has a cosine of 11 over 15. The cosine of the angle whose cosine is 11 over 15 is this angle right here, or this angle right here. So how do you know which one is right? Well, it comes down to the domain restrictions. The domain restrictions on cosine were 0 to pi. So in finding the right angle to answer this question, I have to look in these two quadrants. That means this one here is not an option. That's it for inverses, although going forward you will be expected to be able to use them. They come up in a lot of different applications, and you will see them in the future as well. So let's call it good for this video, and that's the end of this section as well.